So the next speaker is Elsi-Mari Borelli from Algorithmiq in Finland, where she is the lead biology researcher. And she will be talking about quantum algorithms and use cases for life sciences.
Okay, thanks. I wanted to start, of course, by thanking the organizers for the invitation and also for putting together a very interesting program. I think it's been quite a wide range of topics that we've covered today. I would say from the quantum computing perspective, it's been quite wide and high-level talks that we have heard so far, quite general talks. So now we get a chance to do a bit deeper dive into one specific application area, which is quantum algorithms and use cases for life sciences. Now, as you've already heard today, I think in quite many contexts, there are quite many different application areas when it comes to quantum computing. So you might ask the question, well, why specifically life sciences? And I can give a personal reason, which is that I come from a company called Algorithmiq, and I will introduce it very shortly if you don't know the company. So we are a company, a startup from Finland, and we are specifically focusing in developing algorithms for life science use cases. So that's the reason why I would talk about this topic, but it's not the only reason why to choose this specific topic. It's also perhaps a topic where we can expect to see maybe in short term the most direct applications of quantum computing, and this is something that I will argue a bit more and explain during the talk. But I wanted to start with a reference actually to, I don't know how many of you were actually at the dinner last night, but it's funny that there was this, because I sent these slides a week ago, so it wasn't planned to have this overlap with the speech from last night. But yesterday we heard that all of us are somehow nano, or let's say part of nano, and I'm actually starting the talk with claiming that it's not nano, but it's quantum. So in the end, all life is quantum. So of course, if you zoom in to any living organism, and if you zoom in deep enough, you come into to biochemistry, let's say biomolecules and the chemistry of them that in the end governs how all organisms work. And if you want to make a description of the functioning of these biomolecules, of their chemistry, you need to make a description on the quantum level. And this, of course, is a motivation on itself to try to simulate large quantum systems in order to simulate biomolecules just for the sake of understanding. But besides understanding, this, of course, has very important implications for industries such as pharma, for example, discovering novel drugs. You know, if we would want to use computers in order to simulate and know let's say on a simulation level whether a drug will work, whether it will bind to a specific molecule, for example, you would need to do a quantum level calculation simulation in order to see this. Now, this is something that, of course, has been known since the discovery of quantum mechanics. And for example, already in 1929, Paul Dirac wrote that the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known, knowing quantum mechanics, of course. And the difficulty lies only in the fact that application of these laws leads to equations that are too complex to be solved. Now, what did he mean by this? So if we now take, for example, let's say a quite simple molecule, let's say this is a small drug molecule, penicillin, not at all in the scale of proteins or enzymes if we would want to understand the functioning of something like that. So a fairly small molecule drug. And we write down the electronic structure problem that would describe the structure of this molecule. Simple looking equation, but if you want to actually write that state on a computer, it's like This is already something that Klaus was already talking earlier today of the exponential scaling of this. The exact quantum simulation and encoding this state into a computer would require 10 to the 89 bytes. And now this in comparison, for example, to the computer that maybe will be discussed later today in another context. But this, for example, has 10 to the 17 bytes of storage capacity, and this is one of the largest supercomputers today. So clearly, by far, not enough. And it's not just that, okay, we don't have good enough computers, but if you look at this number, 10 to the 83 actually corresponds to more than the number of atoms in the universe, so we know it's just impossible to ever have a computer that could encode all that state. And this is a small molecule, okay? But this quote actually continues. It didn't end there. So how Paul Dirac saw that this could be solved was with the following. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. So basically saying, okay, yes, its underlying system is quantum mechanical, but maybe if we make the right approximations, if we make a kind of an effective description, we can capture the fundamental part of this quantum mechanics that gives rise to, I don't know, how molecules, for example, work. This is what physicists always do. This is what we do. It's not like everything is made of quantum particles, but we don't make a quantum mechanical description of it. And this is indeed what has been done, and this is what computational chemistry is all about. So, for example, as an example, the Nobel Prize in Chemistry in 1998, just to kind of emphasize the importance of these type of methods, was given for the development of density functional theory and computational methods in quantum chemistry. So basically, the development of density functional theory and other computational methods, approximate methods for describing such large quantum systems, molecules, for example, has allowed to, for example, you can perfectly simulate the structure of water, coffee, penicillin, molecules of this size. You can do that on your laptop. Further, in 2013, the Nobel Prize was given for another achievement, which is development of multi-scale models for complex chemical systems, which doesn't even limit anymore to small molecules as such, but basically allows you to embed only a relevant part of your computation, of the quantum part of your computation, to a much larger classical simulation, and allows you to effectively simulate tens of thousands of atoms at the same time. And for example, understand certain enzyme functions to some level and have a glimpse of this in a simulation level. So this just to say that, of course, since the foundation of quantum mechanics, already computational chemistry has done immense work in being able to simulate already large systems. But still, these methods do have limited accuracy. So we cannot still, for example, model everything that we would in order to be able to simulate, for example, how well drug binding works realistically. And this is because there is still truly some parts of these enzyme functions, for example, that rely on strong correlations that cannot be effectively captured with the methods developed today. These are, for example, in the presence of transition metals in the enzymes, or, for example, when you study light molecule interactions and you're interested in excited state dynamics and these kind of things. Typically, the accuracy of these methods is not simply sufficient in order to make such predictions. And now this is the part where quantum mechanics, quantum computing comes into play. So now it's the time for the maybe one of the most seen quotes around quantum computing by Richard Feynman, which was to say, well, the nature isn't classical, damn it, and if you want to make a simulation of nature, you should make it quantum mechanical. So saying that, okay, if for some part of your enzyme in the end, let's say that you cannot find a good approximation. So you truly have to do really the quantum mechanical simulation. There is no good approximation. You just need to, only way to do it is to solve solve the full quantum mechanical equation. And then in that case, kind of the only way you can do it is to use a quantum system to do the computation itself. And that's where quantum computing comes into play. So, in practice, how would one address such a problem on a quantum computer? So as we said, the problem is the following. We have some molecule, and we have the electronic structure problem. What you do is that you encode this problem into another Hamiltonian, which is a qubit Hamiltonian that you can actually simulate on the quantum computer. And then what you want to do is to estimate the ground state energy. And now there are two kind of classes of algorithms on a quantum computer that could be used in order to do this. The other one is known as the quantum phase estimation. And then there is another kind of class of algorithms, I would say, which are more hybrid algorithms, which are mixing some part of the computation is done on the quantum hardware and some part on a classical hardware. Now the phase estimation, this is an algorithm that requires so-called fault-tolerant quantum computing. So to implement this would require, let's say, full error correction. It would require several millions of qubits. And these are something that don't use any classical parts. So they run purely on quantum hardware. Okay, so if we look at what is the status of quantum hardware now, we are, I think this has been also mentioned today, we are in the range of some hundreds of qubits. Let's say the best devices have some hundreds of qubits. And these kind of devices, it's not only about the number of qubits that matter, it's many other metrics that are really important for the functioning of these devices. And these, let's say, multi-hundred qubit devices, they typically have quite high gate error still. They have limited operation speed as well. And okay, the qubits are not fully connected and so on. And the numbers are still limited. But let's say what we can say in conclusion that it's not very close to what, for example, the phase estimation algorithm would require. So it's quite far from it. And if we look at the near future, let's say within the next maybe few years, where would we expect the hardware to get? If we look at, for example, now again, IBM, which has the biggest hardware currently, they are, for example, putting for 2024, so very near future, this 100 challenge, which basically their goal within the next year is to, for this kind of mid-scale devices, so with some hundreds of qubits, to push on the quality, so push down the error rate significantly, and to improve the speed of the devices. So basically, to be able to do some kind of relevant computation on such a device within one day. That's kind of where they're aiming at. But I think what we can conclude is that, okay, you cannot do quantum phase estimation on quantum hardware in the next few years. This will be many years off. So you need to wait at least 10 to 30 years in order to do this. So then the question is, how about these hybrid algorithms? So these are algorithms that are targeted to around, let's say, starting from 10 to maybe some thousands of qubits. They are algorithms that operate even in the presence of noise, so they don't require error-corrected qubits. And they're hybrid algorithms, so they somehow interface with classical computation in order to perform. And this is something that, okay, if you look at the number of qubits, okay, it's some tens to, up from there, we have that. They can have some noise, okay, we have some noisy qubits, so question is, it kind of seems like a match for what the hardware is today. So the question is, okay, we have hardware like that. Why haven't we then already seen a demonstration of, for example, advantage in quantum chemistry with a quantum computer? And okay, I think in order to see this in more detail, you need to first see how these algorithms work. So actually, the functioning principle of such hybrid algorithms is quite simple. You take your quantum device, let's say it has some hundreds of qubits, each of these lines corresponds to 1 qubit. You make some kind of, let's say, a good approximation how your state, your final, let's say, ground state of your molecule could look like, and you construct a set of instructions that you apply to your quantum register. And these are parameterized somehow with here these thetas. These are some parameters that you can change. Then you make a measurement of the energy of that state that you prepared, and then you have some kind of classical optimization loop. So you couple it to your classical computer, and it gives you instructions on how to update on the parameters, and in the end you want to minimize the energy and find the ground state. It seems like a quite simple recipe for finding your ground state. And this is what is often called variational quantum algorithms. The unfortunate thing is that these have multiple problems. And that's why I say that we haven't seen any quantum advantage today. So first of all, one big problem here is that this measurement stage, so estimating the energy, is way too time consuming. So in order to make a good enough estimate for this algorithm to work, you have to repeat it many, many, many times. The quantum computers are still quite slow to operate. So in the end, let's say the time scale that it would to actually implement an algorithm like this blows up. Also this optimization, whenever your system sizes increase, this optimization gets intractable, so you cannot do it. It fails in practice. And perhaps the biggest problem is still that the quantum devices are quite noisy. Whenever you apply these gates, they introduce noise to your system, and this always biases the results and in the end gives you bad estimates. So it doesn't bring you the kind of accuracy that you would need. Now at Algorithmiq, what we are working on is to remove exactly these roadblocks. So we've been working in the last years quite intensely to basically change, it's one part of this setup, which is the measurement part practically, which is just implementing these measurements in a different fashion, which is called, in quantum information theory, it's called informationally complete measurements. But basically changing this one paradigm in this setting allows you to construct new kind of algorithms that basically overcome these bottlenecks of these variational quantum algorithms. So basically, we're able to reduce the measurement to minimize the time of this measurement stage and bring this measurement time down very significantly. We're able to devise an algorithm for doing this optimization without any of these bottlenecks of barren plateaus or other optimization problems that are typically bothering the variational quantum algorithms. And besides this, we're able to perform noise mitigation algorithms that don't have bad scaling when you increase the system sizes, in the sense that you're still able to scale up to some hundreds of qubits for the variational quantum algorithms. But overall, as a conclusion, we can say that, okay, from the hardware side, we see that there is a push, a very strong push, to bring the error rates down to the level, to bring the speeds and sizes up to the level that you could start thinking of applications in quantum chemistry. On the algorithm side, we're pushing very strongly to bring, let's say, the algorithmic requirements to the level that are matching actually what the hardware can provide to us, which would give us the chance of doing something useful in the next few years. But I would say that that's not exactly yet enough. There is still one piece missing, which I think is to find the correct life science applications. Because this is also very important. Maybe it's not all about finding the ground state, you know. All these algorithms are devised to finding, for example, ground states of energies, and you need to find them with very high precision and so on. But in the end, there are problems out there, for example, related to excited states I was mentioning earlier. And for example, when you look into larger systems like enzymes, it's only a very small part of it, let's say the transition metal complex, that you need to treat actually quantum mechanically. And then you need to have good embedding strategies in order to be able to do this, like also in the classical case. And in general, let's say, for us, we need to integrate with all the huge, let's say, huge amount of methods that there are out there already from the quantum chemistry. Why not use the best algorithms that quantum chemistry has to offer already now? And that's another very important effort, and this is somewhere where strong partnerships with pharma and pharma companies and specialists from the computational chemistry become very important. But kind of to put the full picture together, what it requires to actually show any advantage in quantum chemistry is that you need to bring into one package, okay, the actual quantum simulation that is doable, let's say, that doesn't scale badly, that scales in a way that you can deal with hundreds of qubits well. You need to bring the best quantum chemistry together. You need to have the right quantum hardware, the best quantum hardware available, and you need to couple this to the best high-performance computing as well. And what I would say that if you put all this together and ask the question, okay, how far are we truly from some practical quantum advantage where we can start seeing some real applications in quantum chemistry, I would say that, okay, if we push hard enough from all the sides at the same time, so we as we are, let's say from the quantum hardware side, from the quantum algorithm side, and we really connect this together with the life science applications simultaneously, then we can actually, within a few years, reach the practical quantum advantage. That's all. Thank you.